So I'm very happy to introduce my old friend Kartik Sheth, who is a manager at NASA headquarters who came from astrophysics science land. He's also been very interested in equity and diversity issues and will come back in the first week of October to lead a workshop for us. So he would have been normally the Srivasta visiting whatever that thing's called that the grad students organized. That was all organized until it was clear that he couldn't come, and then we delayed and delayed, and then we decided to try to do it virtually. So part of that is the person who does the equity workshop also gives a science talk. So this is the science talk from Kartik. I sent a bio around so people should know roughly who he is. If you don't, please ask more questions, but he's going to tell us about his journey from being a scientist to being a manager of NASA missions. So it's all yours, Kartik.
Great, thanks, Douglas. So I should correct any misconceptions, and I'm actually not going to talk about any science specifically in this talk, and really just kind of give you an overview of NASA and kind of how NASA's set up and how it works, and then talk a little bit about kind of my journey from being in academia to why I went to NASA headquarters, and then kind of end with what are the things that I'm working on. I really like interactive talks, and especially in the Zoom world, it is so hard because I don't know, I'm not seeing any of you. So please just feel free to interrupt. I won't mind at all, and just unmute yourself and ask me any questions you might have. Can everybody see the slides okay?
Looks good.
It's good.
Okay, great, thanks. All right, I just put my email and phone number here in case you have additional questions or thoughts that come to you later, or have want to chat. Just let me know. What do you think about when you think about NASA? You might think about the moon landing or the space shuttle. A lot of people will think of the Curiosity rover, and if you're doing astrophysics, you might think about Hubble or Spitzer. And then, of course, the incredible images, especially of the solar system. Like for me, I remember being a kid in Mumbai growing up and getting a textbook from my one uncle and aunt who used to live in America, which had pictures from the Voyager spacecraft, and just like knowing everything about the planets at the time. That combined with the fact that, Star Trek was one of the first American shows to come to India meant I was completely hooked, and what I wanted to do was to go work at NASA someday. So I feel really fortunate and lucky that I have been able to do that. But what I often find is that most people actually don't know how NASA is set up, and so part of what I want to do is to just kind of describe to you, how NASA is organized and what we do at headquarters. So fundamentally, NASA, which we often say, we jokingly call not a science agency, unlike NSF, which we often joke is not sufficient funding. But NASA, not a science agency, right? We're basically a mission-oriented agency. And this is our science fleet. You can see we have an enormous numbers of missions in Earth science. And these are all the astrophysics missions. Here are all the helio missions. And then these are all of the planetary missions. Out of the 18,000 people who work at NASA, only 1,000 of them are actual scientists. And primarily, we are an engineering firm. Our goal is to launch satellites into space and study our own planet and our own solar system and the universe from space. So we often say NASA doesn't do science from the ground. It does science from space, except when we do. The way NASA is organized is we have an administrator who is appointed by the White House. So our current administrator is Jim Bridenstine, who used to be a congressperson from Oklahoma. At the time, he was well known for denying climate change, et cetera. And so we were very, very worried when he was appointed as our administrator, that we were, for the first time, getting somebody who was not a scientist or an astronaut or an engineer. but he has been amazing, I would say. We've all been pleasantly surprised. He's a triple major from Rice University, and he's young. I think he's younger than I am, and just a really, really dedicated administrator who not only has taken the time to learn about science and really speaks for NASA, but because of his connections to the Hill, has been really, really, really fantastic at navigating that fine edge between what the White House wants, what the Congress wants, what the scientists want. So really happy to have him. Down here, you can see sort of the directorates. NASA works on directorates, and we have 4 main directorates: Aeronautics, Science Mission Directorate, where I work, HEO, or Human Exploration and Operation Directorate, and the Space Technology Mission Directorate. And then we have 10 centers. Majority of the people who work for NASA work at the centers. The biggest of these centers is Goddard Space Flight Center, which is in Greenbelt, Maryland, about half an hour from NASA headquarters. Probably about 10,000 people work there. And out of the 18,000 or so people who work at NASA, I would say roughly half of them are civil servants, and the other half are contractors. So a lot of our work really gets done by contractors who sometimes you can have an entire career as a contractor and never be a civil servant. And we have many, many of those. You will see that most of these centers are also near universities, and so there's really good connections with universities, and they're closely tied together. In addition to these directorates, we also have a mission support directorate. They take care of all of the infrastructure, like buildings and water and heat, things like that. But also they have things like the small business program and the protective services, et cetera. And then on this side here are sort of, advisory groups and other areas that are really necessary for an organization to work, like communications, and general counsel, Office of International Relations, etc. Everything in red here is NASA headquarters. That is where I work, and I'll show you in a second what the building looks like and where it's located. Just, it's kind of, I call it the mothership. We effectively send money out to the centers to get the work done. And as I said, we're a mission-driven agency, and our goal is mission success. Everything in the agency is really driven by that. And it is just an incredible place to work. And I'm not just saying that, I've been here 5 years, and it is really the best place I've ever worked in. So this is our building on the top right. It was just recently named Mary Jackson NASA headquarters building, named after one of the famous women who worked at Langley when we were in the Apollo program, one of the human computers, and who were not recognized. In fact, our road has also been renamed Hidden Figures Way. But people found out that Hidden Figures Way was not really, people felt that it was not really specific about naming the people who contributed to NASA, who were really mistreated during the 60s because they were Black, as you probably saw in the movie. And so I think NASA's taking real steps to try to correct the wrongs of the past by at least starting at recognizing what people like Katherine Johnson and Mary Jackson contributed. This is where NASA headquarters is located. As you can see, it says temporarily closed because of COVID-19. I can basically walk to Congress in about half an hour, which is over here, US Capitol, Library of Congress. This is where the White House is. And then you can see the Air and Space Museum, which is also in walking distance. So I live over here. So, I walk to work, which is kind of cool. NASA, like I told you, has been named the best place to work in the federal government. Now we have won that award 8 years in a row, which I find incredible. So just about right after the murder of George Floyd and Ahmaud Arbery and Breonna Taylor, as you know, basically the US and in fact a lot of the world is undergoing, 2 pandemics. One is, we are dealing with the COVID situation and coming to terms with the horrible history of racism. And NASA is really taking some very active steps. I was really happy to see this announcement from our administrator announcing the 5th NASA core value of inclusion. And this is really giving us the ability to start changing many of the processes and procedures and our culture from being a racist organization towards committing to doing more anti-racist things and creating a world that is more equitable and just for everybody. So I think this was really a good step forward. And when we meet again in a month and a half or so, I can talk more about all of the different things we're doing. One of the things I'm doing is I'm serving at the Science Mission Directorate level on a committee, or a group, I should say, anti-racism group, chairing it with my associate administrator. And I'll describe what that means in a second. But so we're really committed to this. So how is NASA organized? So you saw in the past, like up here, you saw that there were these directorates. Now I'm going to focus in on the Science Mission Directorate, which is where I work. So this is the Science Mission Directorate. Our associate administrator is Thomas Zurbuchen, deputy associate administrator is Sandra Connolly, and we effectively have 5 science divisions and 1 sort of a joint agencies division. So I work in astrophysics. Our newest division is biological and physical science divisions. We just came over from Human Exploration Office. They are the ones who really do a lot of experiments in microgravity up on the space station. We're really, really glad to have them because now all of the science divisions are all in one place. Astrophysics, as you know, handles everything from the edge of the solar system all the way out to the epoch of reionization. The Planetary Science Division basically explores everything except the Earth and the Sun. Heliophysics Division primarily explores the Sun, heliopause, the interaction of the Sun with the Earth. And then the Earth Science Division looks at our planet and the Earth system as a whole. I came in after tenure as a program scientist in the Astrophysics Division. You will hear people say, I work at NASA headquarters, and somebody might be called a program scientist or a program manager or program officer. They're effectively interchangeable. When you talk to people at, or program directors, so if you work at the National Science Foundation, they call themselves program directors. The work at NASA headquarters is a little bit different because we're so mission focused. We basically have 2 main roles for most of the people in the Science Mission Directorate in these divisions. You're either a program scientist or a program executive. The program scientists are typically people with PhDs in a particular scientific area. And our goal is to try to maximize the science that comes out of the missions and from research and analysis and technology development. And program executives, who we are paired with typically for every given task that we do, the program executives are typically engineers. They may not have a PhD, and they typically take care of the budgets and making sure that things remain on cost and schedule. And so we are always working in teams. Fundamentally, headquarters is a very, very flat organization, and astrophysics is a very, very small part of it, as I'll show you in a second. So what you do at headquarters is effectively get money from Congress, and you send money out into the community and to the NASA centers to get the missions developed, formulated, developed, and launched. So typically NASA gets roughly $22 billion a year. Science is one of the biggest parts of that. It gets about $7 billion, and the other big part is Human Exploration Directorate. So those are the 2 big directorates that we have. And within science, like I explained to you, there are several different divisions. Astrophysics is one division. And our budget, for example, in FY20, which is fiscal years, by the way, in the United States start October 1. So fiscal year 21 starts this year, October 1, and it will go through September 30th of next year. And right now we are in fiscal year 20, which will end before the calendar year ends. We were allocated $1.7 billion with a B, and pure astrophysics had 1.3 billion, and about 400 billion went to James Webb Space Telescope. And this number that you see here, 796, is astrophysics minus the Roman telescope that was named after Nancy Grace Roman recently, the W1 telescope. So you can see the breakdown here. The items that are listed here are the ones that Congress specifically tends to call out which you might call them earmarks, which you might have heard about, which means that when Congress tells us we're giving you $423 million this year to spend on the James Webb Space Telescope, you can only spend it on James Webb Space Telescope. You cannot take even $1 from that money and allocate it to some other purpose. And that restricts our ability to manage the portfolio. So this $1.7 billion portfolio is run by this team. So it's a really small team, actually. There's only maybe 6 or 7 program scientists who are civil servants. So besides myself, we have Dominic Benford, Dan Evans, Hashima Hassan, Doug Hudgens, Stefan Imler, Linda Spark, myself. Rita has moved on now, but we used to be Rita. And that's it. Everybody else you see here is a rotator. They're coming in and leaving. Typically, our rotations are 2 to 6 years. And typically, we tell people you should at least stay for 4 years because, it takes you a year or 2 years just to learn the system. And then to be effective, you really need to stay another year or 2. Some people are repeated here. You can see Mario is down here and up here as well because he's, in addition to being a program scientist, he's recently been appointed chief technologist. And then our James Webb people are put up here. This is our administrative staff. And then these are the program executives I was talking about. Lucian Cox, Shahid Habib, Jeff Hayes, Dave Jarrett, and Mark Sestili, all of them civil servants. And then the director is Paul Hertz, and the deputy is Jeff Velosin. So between us, we have to manage this $1.7 billion budget every year. And when I was doing my interview, I was really worried. I'm like, what they ask you, what do you have any concerns in your interview? And I said, well, I'm really worried that I have to deal with millions of dollars. What if I make a mistake? And they said, well, have you ever balanced a checkbook? And I said, yeah, I've balanced a checkbook. And they're like, yeah, it's just more zeros. So I really like that answer because, it takes the stress off a little bit. But it is something that you have to get used to dealing with, hundreds of thousands to millions of dollars in your portfolio. Out of that $1.7 billion, this is how the money is divided up. Some amount goes into management and then STEM activation is allocated in there. Research, which is ADAP, APRA, and ATP, those are the things that you can write proposals to NASA headquarters, and that's roughly about $100 million a year. We spend, even though that is such a small percentage of our entire budget, most of the program scientists spend their time in this research and technology area because we have to send out the call for solicitations, gather the proposals, put together panels, collect their evaluations, make sure that they're evaluating them based on the criteria we've laid out. And then a really important task happens where you, as a program officer or program manager, look through what the evaluations are and make decisions based on programmatic considerations. And you end up recommending things that you want to fund. Compared to National Science Foundation, we have a lot more control over our portfolios. We make real decisions, and we don't simply go by whatever the panel has said, because there's always many, many more good proposals per evaluations than we can possibly fund. So there's a lot of thinking that goes through in terms of having a balanced portfolio. Is it really aligned with the science plan we have? Is it aligned with the values that we have? Is it aligned with the missions that we want to create? Then technology here includes SR&T, which is Strategic Research and Technology. So these are directed research where we are trying to take technologies which are called technology readiness level 3 and above. And we are trying to mature those technologies. Like I told you, a lot of what we do is we're an engineering firm, and we are trying to fly missions. And because in astrophysics, everything we do is sort of a one-off, you're often doing technology development for the first time, and you have to really kind of shepherd that all the way through. Athena and Lisa are foreign missions that we're partners on, but they're strategic in nature, so they fall under that. Balloons and archives fall in here, and then you can see this money here, which is 17%, which is operating missions. That's Hubble, Sophia, XMM, Swift, New Star, TESS, all of those missions, and I'll 20% of our money goes into that. And that money typically goes directly to our contractors, like the Space Telescope Science Institute or Chandra Science Center, and then they manage the mission for us once we've flown it. Explorers and development are the next set of missions that we're launching. So things that are coming up like XP or CASE or Ariel. So that's the money for the next generation of missions that are not flagships. And about half of our money goes into flagships, third to a half of the money. And it's never more than this. So right now we're spending all of this money on WFIRST, also known as Roman, and James Webb Space Telescope. In case we have overruns and a flagship is delayed and costs too much money, we try to keep this wedge the same because we want to protect the day-to-day operations of what's going on in our science community and the building of technology. So what we end up doing is the mission simply gets delayed and you end up spending more on it. But we don't cannibalize the rest of the budget to try and protect this part, which is our next future flagship missions. So roughly speaking, you can see we spend about 20% in community support, 12% in operating missions, and then about half in flagships and another 10% in the next generation of explorers. By numbers, this is just a very quick way of, again, slicing our portfolio. You can see every year we get about 2,000 proposals. The success rate is about 20%. We award about 70 million. We have 180 new PIs. It's amazing how many new PIs we have every year. At least half of our PIs are new each year. We spend $140 million in technology, 100 million in RNA programs. We are spending $5 million a year roughly on CubeSats, which is the new initiative that was started last year. Some money goes into sounding rockets. And then, this is one of my favorite things is balloons, especially in the infrared and in the optical. For example, Superbit, which Bill Jones is flying, 60% of all the science Hubble can do, it can do because of the fantastic pointing we can get from the WASP instrument that they can fly, and just the quality of the instruments and the telescope now is so much better than when Hubble was launched. So I think balloons are really an underexploited resource, and I know Canada is really interested in putting more effort into ballooning. So I'm hoping we can carry that forward into the future. This is a quick view of how you might divide up what we call ROSAS elements. ROSAS, think of Valentine's Day. So on February 14th, we published the ROSAS for the next year. That publication has all of the programs that people can write proposals to get money to do a variety of things. So you can do, like I said, ask for technology money. You can ask for money to do theory. You can ask for money to do theoretical and computational networks. You can do exoplanet research. You can ask for data analysis and also suborbitals. Things that are here in red and things that are up here outside are solicited separately outside of the ROSAS call. Here's all of our astrophysics missions that are operating. You're probably really familiar with most of them. And some of these are entering extended operations. So Sophia tests are in extended operations. The balloon program right now is suspended because we do a lot of our flying through New Zealand. And when COVID hit, right, we weren't traveling anywhere. These are the things that we're developing going into the future. So as I said, Webb and Roman are the big ones, but we're building XP, Gusto, which is a $40 million balloon explorer that's going to survey a quarter of the Milky Way in spectroscopy for far infrared ionization lines. We're building Ariel, which is going to be a planet hunter. And then SMEX and MOOS are the next generation of things that we're going to pick, which will either be Cozy or Escape, or Leap or Dorado. Just a very quick word on James Webb. We're super excited, in spite of all the delays, and we realized that, this is going to be one of the most expensive missions we've ever flown. The observatory is nearly there, right? There's, I think, just a few more tests left. We're going to start packaging up. We're working with the military and trying to figure out how we're going to escort the ship through the Suez Canal, and sorry, not Suez Canal, through the through Panama and get it to French Guiana for launch. So I think that's going to be super exciting, and it's going to study not only the first stars and first galaxies, but also be able to study atmospheres from exoplanets. Our main goal within NASA Astrophysics is to have a balanced portfolio. And so one way to look across from left to right here is to say high risk, high investment, high return. And as you go to the right, you're going to lower risk and lower budgets, and maybe not as much return as you would get. And together, by making sure that we are flying across this, we reduce our risk in any one category. And we want to really have all of these things at the same time. So flagships are a national priority. The kinds of science they do will change textbooks forever. Whereas you can get, Nobel Prize winning work with small things like WMAP. The last 3 years, we've spent a lot of time thinking about the next flagship. As you know, the Astrophysics Decadal Survey is going on right now. The community came together and did amazing jobs with the science case and the necessary technology for HabEx, LoopBar, Lynx, and Origins. Douglas Scott, who was one of our STD team members, Science and Technology Definition team members for the Origins Space Telescope, which is a cold cryogenic infrared telescope, which would really be the successor to both James Webb and Spitzer, and really would offer us 1,000 times improvement from anything that we've done before, and maybe 1,000,000 or 1,000,000,000 times better in survey speed. So I'm really hopeful that gets chosen, but what we say at headquarters is we would be really happy if the Decadal Survey really picked any of these, but also really we hope that they endorse all of them and simply tell us the order in which we should build them, from the far infrared Origins telescope to the X-ray telescope called Lynx, and one of the two UV optical telescopes, the HabEx, which is the smaller one, and LoopBar, which is the really large one. Okay, so now I'm going to kind of switch gears and talk about, I hope that's a good overview of NASA headquarters and what I do, and I'll end with what I do in my portfolio. But I just want to go back, especially for the undergraduates and graduates and the graduate students in the room. This is what you're told, right? When you start your career in science, like, do well in high school, get a great GPA, maybe even start doing some research, go to a good undergraduate school, maybe write 1 or 2 refereed papers, ace the GREs, at least in the US, and then, go into a prestigious graduate school. Then maybe after going into a prestigious grad school, you want to go into a postdoc at another top tier place, become a faculty, get tenure, become a full professor, and so on. So this is this perfect single trajectory. And what I'd like to tell you is that this is like, you should banish this out of your mind, right? Very few people can really stay on this trajectory. You have to be incredibly privileged, lucky, and just, to do that. And life will throw curveballs at you. And, I think we're just very privileged to be able to do science. And so, I think you should think about every day as just being fantastic, because you're able to do something that most people can't do, that you're paid to do, a hobby. But don't like kick yourself if you're not on this trajectory, because things will work out. So, just a brief bio of myself. I grew up in Mumbai, like I told you, dreamed of being an astronomer, emigrated to the US at 14. And then I did my undergraduate in physics at Grinnell College in Iowa, and was very, very fortunate that my advisor would never sign my card, my transcript, if I took more than 2 math or science classes. And so as a result, I really learned a lot of critical liberal arts skills. Then I ended up doing horribly on my GREs, and ended up getting waitlisted at the only school that would accept me, which was University of Minnesota in Twin Cities. And I almost dropped out there because I ended up in an incredibly racist, sexist environment. And I thought I was not good enough to be a scientist. And I didn't want to be in the science environment because it was so toxic. My professors convinced me that they'd prepared me well enough. And I went back, decided I would end with straight A's, pass my qualifiers. I ended up doing a master's in physics education, which I, to this day, really value that experience. I did pass my quals, got straight A's, but I had long since made a decision I was going to leave. And so I applied, again was waitlisted at University of Maryland in spite of quadrupling my GRE scores, which tells you how bad they were the first time, and just had an awesome time at University of Maryland. Partly doing graduate school a second time was really good for me because it allowed me to just excel. And because I grew up incredibly poor, in India, my goal was to get a permanent job as quickly as possible. So I ended up really only applying to 4 places for postdocs because I figured if I couldn't go to one of those, I should go do something else with my life. So I only applied to Caltech, Harvard, and Berkeley, and the Hubble Fellowship. And I was fortunate enough to get a postdoc position at Caltech, working with the Owens Valley Radio Observatory. And then I really wanted to get a real job, quote unquote, as quickly as possible. So very soon after that, I became scientific staff, also at Caltech, and I was the instrument scientist for the infrared spectrograph for Spitzer Space Telescope. And every time I got a job offer, Caltech kept making me a counter offer with more money. So I turned down 3 or 4 faculty offers in that time there. And then eventually in 2009, as ALMA was coming online, NRAO recruited me. And it was a chance for me to move back east, closer to my parents. And so I moved to NRAO in Charlottesville. But I was also commissioning and science verification liaison for ALMA in Chile. So I spent 2 years on and off living in Chile. Really, I was there when we had phase closure for the first night at the high site, and we celebrated with plastic bottles of water because it's a dry site. And it was just such a pleasure to see ALMA come to life. And it's so awesome to see how incredible it is doing today. And then I also, as I will show you in the next slide, really passionate about issues of equity and justice. So I had suggested and recommended we start a diversity and inclusion initiative. I started 2 programs called NAC and 9, both intended to try to get more students from underserved, underrepresented groups into STEM. And eventually in my last year, they also appointed me, they established the Office of Diversity, Equity, and Inclusion, and then I was the first director for that. But I had a horrible time in Charlottesville, as I will tell you. And then as soon as I got tenure, I decided, okay, I've achieved everything I want to. I'm gonna skip this and go do something totally different. So I decided to go after I got tenure to NASA headquarters. So I got tenure in 2014, went to NASA headquarters in 2015. So my astronomy background is, I've done a lot of research in galaxy assembly and evolution, overall cosmic time. I would say I'm an expert in barred spiral galaxies and using bars in multiple different ways over cosmic time as a signpost of galaxy evolution, but also really using it for understanding molecular gas and star formation. And if you look at my scientific papers and research I've done, it spans everything from putting in proposals to study Trojan asteroids around Jupiter to star formation and the interstellar medium in nearby, all the way to the most distant galaxies, and including even the first paper on a radio curve for 030329 GRB, where I worked with Sri Kulkarni. And this really prepared me well for a job at NASA headquarters, because Leo Blitz had told me once very early on in my career that you should be interested in all astronomy. And I really took that to heart, and I've really enjoyed it. The downside of doing something like that is if you do that, people in academia can't put you into a box, and it actually makes it a little bit difficult for you to get a permanent position. So just be warned, But I still think you should chase whatever you love doing, chase passion, and don't chase success. Because if you chase passion, you will be successful. I really was never designed to be an academic. I really don't like the faculty lifestyle personally. So I always chose a career that was more service-oriented. And I really enjoyed working in groups and teams. Those are all the different teams I've worked in, including running some of my own. I was a founding member of SONG, founding member of Cosmos, and PI of 2 big legacy programs with Spitzer, S4G and S4G+. And I loved the idea of working in teams where you work with engineers to try to make things as efficient as possible. So, I love this little cartoon, Good News Cecilia. I have a good lead for a faculty position for me. And you can see, she says, me, a professor? Of course, isn't that why you came to grad school? And we all go through that, like, I don't know if that's what I want to do, And then the funny thing is where the professor says, well, at this point, that's what your only job you're qualified for. And a lot of us, if we choose the academic life, are going to face this incredible mountain where there's just a lot of uncertainty and a lot of perils along the way. I just really wasn't a big fan of this. And so for me, I just, when I got tenure, it was really, really good time for me to leave academia. I had a fantastic 9 years at Caltech. really just had lots of fantastic offers. You know, the thing I still regret to this day is turning down an endowed chair position at University of Cape Town in South Africa. I loved working on traveling all around the world. I had an amazing group of postdocs and students. Two pride and joys are starting the National Astronomy Consortium and the exchange program in South Africa. Got to design and build my own house from scratch, which was also a great achievement. And really, you know, working on the last Obama campaign or the second campaign, getting to meet the president and being a precinct captain were just really fantastic things that I loved in Charlottesville and Caltech. But the bad things were, I hated the culture at NRAO. There was internal strife between people who were called tenure track and astronomers. There was a lack of a growth mindset. There was really no support. Something bad happened to me probably every week because I was a brown person living in Charlottesville. And scientifically, I kind of felt like I'd achieved a lot of my career goals in terms of the number of papers I wanted, citations, grants, etc. And I found myself going from one windowless conference room somewhere in the world to the next windowless conference room somewhere in the world, talking to the same people. And the amount of science advancement was just so minuscule. So I was super bored. And in 2013, just by luck, somebody asked me to serve on this committee called Enduring Quest Daring Visions. And that opened up a whole new world for me. This is a committee that I worked really, really hard on. We produced this roadmap that I would highly recommend everybody read. It's written at a very, very basic level. And it really has set the stage for the next 30 to 50 years of NASA astrophysics. And just, 18 of us in 9 months created this document. And it was just so much fun that I was like, oh, maybe, I'm really interested in strategic thinking. So that's what I want to do. So even though I was up for tenure in 2014, while going through the tenure process, I was also offered another chair position. But you always kind of feel like you need a backup plan just in case you don't get tenure. So I applied for science policy positions at both NSF and NASA. I was given tenure in October and November. I was appointed, director for the Office of Diversity and Inclusion. But in the same week, in fact, on consecutive days in April, got offers at both NSF and NASA. And after thinking about it for a few days, Paul Hertz called me on Friday of that week, and he said, Kartik, Jim Ulvestad at NSF is waiting for you to turn down his position. And it was really, even though I've done a lot of work in the NSF world with ground-based radio astronomy and ground-based telescopes, I'm really happy to be at NASA. What does the job at NASA involve? Really, like I said, it's the best job I've had to date because I sort of feel like all of that science knowledge I learned, all of those liberal arts skills I learned, I can now apply them to do good for our community. So I would say I spend about 70% of my time doing strategic thinking, really thinking about what small decisions and policy changes can we make today for the betterment of the field and the betterment of the scientific community. We probably spend about 20% in panels, putting panels together. I find that really boring. I'm just a missions person. I love observatories. I love trying to figure out how to extract the best science out of that. So I love doing that. And I probably spend, at this moment, I'm probably spending 100% on inclusion issues, but overall, maybe 10%. And this is my portfolio, and it's very, very broad. And so I'll just tell you the things I'm working on right now. Right now, I'm working on multiple things in the Science Mission Directorate level. I'm running requests for information from the community on whether there might be gaps that exist in interdisciplinary, interdivisional work. And I just, in fact, reported on it this morning at 8 a.m. our time, so 5 a.m. your time. I'm serving, like I said, as a co-chair on this anti-racism committee, and we're trying to take really powerful actions immediately because we can't not take action towards a more just NASA. Just ran an agency innovation workshop, which was a lot of fun, and we're working on that and looking at science and technology partnerships, which are with Space Force, DoD, US Air Force, and possibly other agencies on what technologies that we are interested in common, and also working on the diversity inclusion working group. I also run the Cosmic Origins program. That is the entire program that looks at everything from Kuiper Belt to the epoch of reionization in terms of science. We are trying to answer the question, how does it all work? How did we get to today? And in that program, we are trying to connect with the community and oversee all of the science that is done, answering that one of the main themes. I previously used to run the Spitzer Space Telescope, but of course we turned it off last year. I ran the Origin Space Telescope mission concept study. I am the deputy program scientist for Webb, run the Hubble Fellowship Program, and the ARA discipline scientist. In October of last year, I also kind of got bored with astrophysics, felt like I'd learned everything and wanted to do something. Climate change is a really existential threat for a lot of us, and including for me. So I felt like I should use my science skills for good. So I've been doing a detail in earth science and applied science, where I'm managing a consortium called Valuables, which is a group of economists who I work with and I oversee, who are trying to figure out a microeconomics approach to valuation of earth science, earth observations for socioeconomic benefits. I'm working with the ecological forecasting team on United Nations Sustainability Development Goals 14 and 15, and also went to the World Urban Forum, which was sponsored by UN Habitat, on cross-cutting urban issues for SDG 11. And then I also work on a cross-agency working group with USGS, which is United States Geological Services, and NOAA, where we are trying to put together a repository that is addressing the third goal from the national plan, that we need to have a national repository for evaluation studies, and serving on the GeoVal group, which is a working group that is actually run by a Canadian person named David Haight. And we're putting together a workshop on sort of the economic valuation of the benefits of Earth observations. So I'll stop there and just take questions. I'm sorry, I know it's a lot of information. I hope that was valuable to you.
Oh, that was great. Thank you, Kartik. That was, I mean, I learned a lot.
Good. Let me turn on the light here. Give me a second.
Yeah, I'll say to you later, maybe.
Okay.
Stories about these people that would be entertaining to share. The first question that appeared in the chat was, you presented the sort of organogram for NASA, but how does a place like JPL fit in?
Yeah, really good question. So JPL is not actually, we call it a pseudo NASA center. It is actually a contractor for us. They're run by Caltech, but we treat them like a NASA center. And in some ways, they have the best of all worlds and the worst of all worlds. Everybody who works at JPL can be fired at any time. So unlike NASA centers where we have civil servants, JPL people are all contractors. However, we treat it like a center in the sense that we make sure that there are certain capabilities that are unique to JPL, and we want to continue to foster them. So in some sense, they do get some directed work. And it's always a negotiation, right? In astrophysics, there's always kind of a battle between JPL and Goddard, because those are our two centers. But we want those two centers to exist because we want them to compete against each other and kind of be counterbalances to each other. The rest of astrophysics is really done at Marshall and Ames, and the other centers are not involved. But for the other mission directorates, like Earth Science, they use Glenn and Langley more than other centers.
And then there were a couple of questions about liberal arts classes. So I think not all science students think that liberal arts classes are all really great. So what did you take that you particularly enjoyed?
Yeah, good question here. Let me see if I can go. Okay. So I think these are the transferable skills, right? So I really love thinking strategically about a problem, and I believe that real advancement in any area comes when you try to bring things from outside of the box that you've grown up in. So what I like about liberal arts are all of these things, right? Ability to think and evaluate things critically. Most importantly, what liberal arts did for me was it forced me to read a lot of different things and be able to coalesce all of it very, very quickly. That's a hugely important skill that you might think, oh, why does a scientist need that? But it is so useful if you can browse through AstroPH every day, skim it, and still get the most important things very quickly. But now imagine that, you're working in some interdisciplinary area, or you have to worry about one of your projects being canceled, and you got to be able to talk to somebody on the Hill, or you need to go to a donor, even if you're in academia, to talk to them about how your science is important to them. Well, you better be able to read and coalesce a lot of broad, different kinds of interesting information, and combine it into something that can be expressed, written, or in oral word clearly and concisely. So to me, that's what liberal arts really taught me well. And I think these are all the transferable skills that I learned in liberal arts. And I think I may have one more slide after this. Yeah, so this is just for the undergraduates, I would say. If you are thinking of, what should you do? I would say chase passion, not success, as I said. When you're in graduate school, these are my bullets that I usually tell people they need to pay attention to. Be the best scientist you can be. Okay, but don't think that, somehow that is going to be your future, that perfect trajectory. Be the best scientist you can be, because, that will allow you to maybe open up doors for you in other areas. I would highly recommend for those in PhD program to read a PhD. It's not enough. And if you can read 7 Habits of Highly Effective People, I highly recommend that. Another book not on here that I would highly recommend, because I get tired of reading crappily written papers, is called Towards Clarity and Grace by Joseph Williamson, where they show you exactly how to take really obfuscating, horribly written academic prose and putting it into simply written and better written language. So I would recommend that. And then think about the fact that, at least in the US, only 10% of the people who get their PhDs can work in an R1 institutions like UBC. 90% of the people who get their PhDs end up somewhere else. It could be liberal arts places. It could be in an observatory. It could be in government. It could be in the financial sector. So, you do need to develop those transferable skills. So just do pay attention to these, right? Like, these are the skills you need to develop. A lot of them you can get as an undergrad with a liberal arts education. And then you can really specialize when you go to grad school.
Are any of those, I know there's other questions here, but are any of those, I would think of all of these as things we get out of a science education. So I'm sort of surprised that you're saying that they're a liberal arts. Yeah,
I personally, when I've dealt with students who've come from heavily science only curricula, they have gathered these skills of being able to look at lots of different areas and, bring their ability to understand art and history and sociology. And that's a different way of looking at the world than the way scientists look at the world. I'll give you a really simple example when it comes to anti-racism. You tell people, oh, there's a problem, right? Oh, where's the data? And then, we're scientists, we're data driven. And then you say, okay, well, and then they automatically jump to a solution and they want to solve it right away. Well, that's not how humans work. So I think one of the key things that you can learn from liberal arts by learning history and art and philosophy is just a different perspective on evaluating the world around you, because at the end of the day, we're still people. And if you just focus on the technical and the scientific aspect of learning how to solve a problem, I think you miss out on other ways of looking at the same problem.